Hello and welcome back to our Geospatial Deep Learning tutorial series. In the previous video tutorial, we learned how to model above ground biomass density using a shallow neural network. In this tutorial, we are going to learn how to model above ground biomass density using a one-dimensional convolutional neural network. So we are going to use the TensorFlow Keras library in Colab. So let's get started. I'm not going to set up the environment and importing the libraries because we have done this in the previous video. So I'm going to skip this initial part. So if you're unclear, please watch the previous video on the shallow artificial neural networks. Right, I'm going straight to the data preparation, especially the splitting of the training datasets. Right, so first here, we are going to scale the input features using the min-max scalar. This is from Scikit-Learn. So this scalar transforms each feature so that they fall within the specified range between 0 and 1. So scaling is very important in deep learning because most of the models generally perform better and converge faster when the input features are normalized. So we are applying the scaling to the selected features in the data frame. So this is our data frame. So the features are from the Sentinel-2 bands and the vegetation indices. Okay, so next we are going to separate the features and the labels. So the labels just refers to the target variable, which is above ground biomass density. And the features, these are the predictor variables, the Sentinel-2 bands and the vegetation indices. Right, so we convert this into the NumPy array. And then after that, we are going to reshape the features so that they are appropriate to be fed into a convolutional one-dimensional framework. Right, then following that, we are going to split the dataset into training and testing dataset. So 80% of the dataset is going to be used to train the model, while 20% is used to evaluate the model. Right, next we are going to build and train the 1D convolutional neural network model. So again, here we are using the Keras functional API. So we begin by defining the one-dimensional convolutional neural network. First, we specify the input layer by calling the input here, and this is going to define the input data, where this x shape is the number of features, and 1 represents a single channel for each feature value. So this setup is necessary so that we can run the one-to convolutional neural model, and then we can correctly interpret the structure of the data. Okay, next we are going to apply the first convolutional layer using the conv1D. So we set the number of filters to 64. So this means that the network will learn 64 feature maps. So we are going to use a kernel size of 2 So this allows us to capture the patterns between the neighboring features. And the activation here is ReLU, which is the rectified linear unit, which introduces nonlinearity and helps the model to learn more complex relationships. So after that, after the first convolution layer, we here introduce or we apply the batch normalization. Okay, so this batch normalization normalizes the outputs of the convolution, so making sure that the network is more stable, and then that it can accelerate by reducing the internal shifts. So following the batch normalization, we add a second convolutional layer. So in this layer, we reduce the filters to 32. Again, the kernel size is 2, and then we use the activation as the ReLU here. So to help prevent overfitting, we are going to apply the dropout, and we define it as 0.3. So this randomly drops 30% of the neurons or units during each training step. So this forces the model to learn more robust patterns. Right, so after these first two convolutional layers, this one, we flatten the output using flatten. So this operation transforms the multi-dimensional tensor into a 1D vector. So it prepares it for the fully connected dense layer, which is the next layer here. So here we just add a dense layer with 64 neurons, and the activation function is again ReLU. So the activation functions further process the flattened features, and it captures the higher level representations. And then to further regularize the model and prevent overfitting, we are going to apply another dropout layer with a dropout rate of 0.2. So this means that 20% of the neurons will be randomly dropped during the training phase. Right, so this is a part of the layers that we have in our 1D convolutional neural network. So finally, we have our output layer here as a dense. So this is going to just create or output a single value. So remember, we are predicting above ground biomass density. Right, so this is this output is appropriate for a regression task, since we are predicting a continuous variable like above ground biomass density. So once the layers are defined, we can assemble the model by specifying the input and the output. Okay, so this is now means that the model is ready. Right, so next we want to better understand the structure of the one-dimensional convolutional neural network. So we are going to create a visual diagram of the model structure. So first here we are going to import the plot model function from TensorFlow's module, from TensorFlow Keras utils module. So this function is designed to generate a clear and a detailed graphical representation of the Keras model. So after importing this function, we can call the plot model, and then this is going to be used to display the model. Right. So as you can see, this is the output showing the model. So the output shape, and then we have the input, the convolutional, the layers, and then we have the batch normalization, another convolutional layer, the dropout, flattening, the dense layer, and another dropout. So this is just the model structure. Right. Next, we're going to compile the model. Okay, so what we do, we are going to use the model compile function. So in this function, we specify the optimizer. So the optimizer here is Adam. So Adam is a very good optimizer because it combines the advantages of other two methods. So in this case, we are going to combine the other grant and the RMS prop. Okay. So we are also going to define the evaluation metrics here. So we are going to define the mean squared error, MSE. Since this is a regression problem, our variable is continuous. And we are also going to track, we're also going to specify the root mean squared error so that we can track how the model is performing during the training. So RMSE, root mean squared error, is better than the MSE because the units of the targets, in this case the units of the above ground biomass will be the same. So it's much easier to interpret. But following that, following the compilation, next we are going to train the model. So before we start training, we need to set up an important callback function here, which is the early stopping. So this helps us prevent overfitting. So we define it using the tf.keras callback. Right. And so in this setup, we are going to monitor the validation loss, which measures how well the model performs on unseen data after each epoch. We set here patience to 20, meaning that the training will stop if the validation loss drops, if the validation loss does not improve after 20 consecutive epochs. And in addition, we are going to use restore best weights to true, so that the model will automatically restore the weights from the epoch that achieved the best validation. So this ensures that we get the most accurate version of the model. So with the early stopping in place here, we move on to the training model using the model fit. Okay, so we're going to use the model fit function. We pass the training features x underscore train, and the target here y underscore train. And then we specify the validation dataset here as x underscore test and y underscore test, so that the model here validates on the test after every epoch. And we set the batch size to 32 here, meaning that the model will process 32 samples at a time before updating its weights. And the epoch here is 300. So 300, which is the maximum number of times that the entire training data will be passed through the model. Okay. although we have the early stopping here, the model is unlikely to finish at 300. Maybe it will finish early because of this early stop. Right, so if we run the model, we are going to now start to get this visualization. We are getting, as the epoch runs, we get the loss. Okay, we got the scores, the RMS scores for the validation, and it runs until the model stops. Right, so the model stops at uh, 135, at the epoch of 135. Right, so it didn't complete the 300 epochs. Right, so following that, we are going to we are going to evaluate the model performance. Just one thing before I move on. So for the deep learning models, especially those with many layers and parameters, there's a big tendency to overfit. So if we are allowed to train for a long time, overfitting happens. Okay, so this is why we're using the early stopping. So early stopping prevents this overfitting by monitoring the validation loss during the training. So when the model stops improving on the validation data for a certain number of epochs, so the training is automatically stopped. Okay, so this is why the training stopped here at 135. So this ensures that the model is captured at the point where we have the best performance, just before overfitting starts. Right. So early stopping is very important, especially when we don't have a lot of computational resources. Okay, and this is going to save a lot of time for training. Right, so following this, we can now evaluate the model performance. We start by plotting the training curves. So this code is going to give us the training curves. As we can see, the model is doing very well. As the validation RMS is very low when we compare to the training RMSE, and there's a point that these two are converging. So this is the point that the model stopped. So performance is quite good for this dataset. So now let's test how this model is performed on the test on the test dataset. And here we're just simply going to call in. We're simply going to predict the model. So we take in the test dataset, and then after that we are going to produce the evaluation matrix. So for the evaluation matrix here, the R squared is 0.5. So this is much better as compared to the previous shallow neural network, where we had a R squared of 0.4. And the MSE is 0.032, while the RMSE is 0.179, which is quite low. Okay, it's very low. This means that we are getting a very good RMSE score for this dataset. And then if we plot the dataset, we see this kind of correspondence, which means that the model is doing actually good work. Although the R squared is a bit low, the model fit actually looks quite good. Right, so this is quite impressive because there's a big improvement in model performance when we compared with the shallow artificial neural network. So finally, we are just going to predict to use the model in order to predict above ground biomass, and then we use that prediction to create an above ground biomass map. Right, so this is our result. This is the map showing the prediction. So range is between 0 and slightly above 100. So it seems there's a bit of over prediction here in this model, because remember our range is usually between 0 and 90 for the model. In fact, I didn't specify. Yes, we specified here. But otherwise the prediction is looking much better, much robust than the previous model. Right, following that, we can save the above ground biomass density map and then export it to Google Drive. Right, and after that you can visualize it in your favorite GIS software, QGIS or ArcGIS. Alright, so this is all about this tutorial. We have learned how to use the 1D convolutional neural network, mostly on this kind of data sets. Right, I hope this tutorial is a good introduction now to the fully convolutional neural network that we will be looking on from the next tutorials. Right, so thank you very much for watching. I see you in the next tutorial.